Thank you very much. Thank you for the introduction. I'm just going to present you the result of the work. Actually, we wanted to find the origin of the zero energy modes, which we found in point contact spectroscopy in topological crystalline insulators. So the paper has got many authors because it has been orchestrated experimental effort to find what's going on. That actually the hunt is still on, as I'm going to show. So let me start from the first slide. Tin telluride is a canonical now topological crystalline insulating material, and this TCI materials, it is actually the symmetry of the unit cell that ensures topological protection. However, this protection is maintained only on highly symmetric planes. So it can be 001, 011, and 111. Tin telluride crystallizes in rock salt structure, and actually what is very important, it has got many relatives, so we are able to actually mix this material by changing anions and cations, and I'm going to use this trick during the presentations. So, for example, as I said, it is very important since we can change either the cations or the anions on this compound. In particular, we can change lead or change lead with tin or selenium with tellurium. Very importantly, when we are switching between lead telluride and tin telluride, actually we have to change the order of the bonds. So on the way from first compound to the second compound, we have to come through the transition here. So we are going from the trivial case for lead telluride to the topological protection in tin telluride. Fine. And actually we can change the properties of this material not only by changing the chemical composition, but also by changing the temperature. Also we can use hydrostatic pressure. So for example, on the left hand side on the slide, we see the phase diagram for these materials. Over there we see the results of the studies. This is ARPES studies, which actually show that when we go from room temperature, which is here the material is in trivial case, we go to low temperature when it changes to the topological phase. To have this phase change around, let's say, 100 Kelvin, we have to use a mixed compound which contained, as far as I can see, 77% of lead and 23% of tin. The next very important part of our study is that these are actually, we are studying bulk crystals, and it has been elaborated more than 15 years ago, a growth method in which we are obtaining macroscopically large crystal of very high quality, and as you can see, they can be easily cleaved into giving us mirror-like surfaces of very high quality, and particularly that kind of cleaving can be done at high vacuum, which actually enables the ARPES studies. Fine. As I said, these crystals are of a very high quality. They are actually one of the kind. The other growth technique can use these results as a kind of benchmarks. All high resolution X-ray diffraction and powder diffraction really confirm very good crystalline quality of our structures. So our technique to probe the system is soft point contact differential conductance spectroscopy. So we use three terminal measurements, and the point, this soft point contact, is done using just very thin 15 micrometer thick gold wire and silver paint just to attach it to the surface, one of these fantastically mirror-like surfaces of this material. And what we see in the spectroscopy, we see something which is very, very characteristic. So, well, depending on the contacts, depending somehow on the days, because these contacts have to be trained or prepared to work properly, we see a structure which has two very characteristic features. First of all, it has got a width. For example, the orange one has got peaks which very nicely mimic the high density of states which we can find in tunneling to superconductors. And apart from this, at the center, at the zero bias, we see a very well defined, very strong structure. So somehow the system told us that we must have superconductivity, and also, which was quite new to us, we did not expect it, and secondly, we got a very stimulating evidence of the presence of zero energy modes. You know, because they don't see it. Okay, so these modes are actually very robust. That was another surprise for us. For example, they can survive with the temperature, well, to more than 2 Kelvin. Concerning the magnetic field, they can survive up to 2 Tesla. And this is, okay, so this is the first experimental results, I mean this one. So the direct 4-probe measurements test of the electrical conductivity does not show existence of transition, the presence of superconductivity down to the lowest temperature. The noise of these results reflects the fact that we use the lowest possible current simply not to overheat the sample, just to be able to pick up a signal that we would be able to analyze. So, if this is supposed to be the conductivity, so what we may have? First of all, we may have, and we have to exclude the presence of superconducting precipitates. After all, a material, a compound, consists lead or tin, so precipitates of any of these could be source of superconductivity. Another possibility could be a tip pressure-induced superconductivity, which I will show you is highly unlikely. Then we may have probably superconducting dislocations. This is still an open question, and some other possibilities are also possible. Good. So, to search for these superconducting precipitates, we start from high-resolution transition electron microscopy. And, I mean, going down to 20 nanometers, like in this image, I mean, we see none. And to some extent, you can trust me that if in this system there are precipitates, they can be easily seen by these techniques. You can also make elemental scans, and I mean, there is no indication that anywhere in the sample there are conglomerate rich in either lead or tin. If this didn't work, so we use squid magnetometry, because if there are superconducting precipitates, we should see them as a diamagnetic shift. And this is an example of lead telluride, and these are the studies more than 20 years old. The material was grown by completely different method. It's also bulk samples, where clearly you see an onset of diamagnetism at the temperature which corresponds to the critical temperature of lead. So if there are precipitates in the material, we should see them. And in fact, we can take, because there are, I mean, I didn't go into this detail. There are limits within which we can mix the elements in this compound. And for example, when we increase the concentration of tin above 37% in selenium compounds, we've got precipitations of lead and tin. And for crystals like this, we indeed find a clear evidence that both lead and tin precipitated. But these are the different samples. So we knew that the precipitates were there. So we took this sample as a kind of benchmark for our technique, and we started to look for similar effects in the materials, which we study in soft point, in the soft point contact spectroscopy, and we didn't find anything like this. Actually, to boost the sensitivity of the squid magnetometry, we use a trick that this morning was described in detail by Dr. Katarzyna Gaz. Namely, we used sapphire strips, which were 8 centimeters long, and they were placed on the sample holder to create a gap. And so the gap in this long sapphire strip actually creates a compensating moment, which compensates the diamagnetic signal of the host of this sample. So we were able just to set the gap accordingly to have in squid the diamagnetic signal, the native signal of the lattice of this material compensated at low temperatures. So in this settings, we did the measurement. So basically, we saw nothing, or if you like, the residual slope that we pick up on one sample corresponds to precipitate concentration no greater than 0.01 ppm. So by this method, we boost squid sensitivity for bulk sample by about factor of 10. So within this sensitivity, we didn't find any precipitates. Okay, so this is a confirmation that we don't see precipitate in high-resolution transmission spectroscopy. So how about these features? Are they ubiquitous, or maybe there are some limits? And in fact, yes, they are. We didn't find any structure like this in when we made the contact to a material in the trivial phase. They had to be, the system had to be at topological phase, and then we were able to see these things. So our statistic is the following. We tried 10 out, so in 10 attempts to trivial cases, no zero bias conductance peak was found. We tried up to about 100 contacts in topological case, and in 95 of them, so let's say in 95%, we found these features. So it is a strong indication that the topological nature of this material do have an important role. Simultaneously, not observing any peak in trivial case rules out the tip or pressure-induced superconductivity. If we induce superconductivity here, we would also induce it over there. So we ruled out this possibility. So what's left? So in our final attempt, we decided to change strategy. So if we were not able to find superconductivity, we decided to kill it. And the best way to kill superconductivity is just introduce global ferromagnetism. And actually, it can be done in this material by introducing manganese. So when we introduce manganese in percentage concentration, long range ferromagnetic order is 4. And we simply hope that in the samples containing manganese in ferromagnetic phase, there should be no features like the one that I was showing you. And in fact, these layers, so when we add manganese, they are ferromagnetic. So this is, for example, temperature-dependent studies. So for 10%, so if we add 10% of manganese, actually it has been read like this: the total concentration of cations, I mean the total amount of cation atoms, is the same as the anion. So the total is 1. Okay, so if we get 10% of manganese in this compound, the Curie temperature is of the order 15 Kelvin. When we use only 3%, then it's much lower, it's about 3 Kelvin. And the same is also seen when we measure magnetization versus magnetic field. We see a clear ferromagnetic case. For the samples without manganese inside, the signal is diamagnetic, is much weaker. Please note that the scale here is changed 10,000 times. So this is basically 0 on the same scale as for the samples co-doped with manganese. And we see the same features. So presence of manganese, which made the samples ferromagnetic, didn't change a thing. We still were observing very nice, very strong features, and also the zero bias conductance ping was clearly observed. Okay, and just to somehow summarize our finding, it is not only that the presence of ferromagnetism did not kill this effect, which we somehow have to connect with superconductivity. Actually, they are much more robust. They are much more difficult to be extinguished. So in this case, they survive up to 5 or even 6 Kelvin, and also the magnetic field up to 1.5 Tesla. So this is quite a remarkable thing, that we observed features which are like for a material with superconductivity in bulk material which is truly ferromagnetic. We can just perform either magnetic field studies or temperature studies, and we clearly see that there is a phase-like transition behavior for these features. They follow a typical scaling expected for BCS superconducting theory. So they follow it very nicely, and I must say they clearly they don't take any respect if the system is ferromagnetic or paramagnetic. They simply follow this train. There is one weak point, I would call it, the prefactor which is present here, which should be below 2 for BCS weak coupling, is of the order of 4 in our samples. So it's not exactly the BCS, but it is very similar one. So the last one, what I just want to show you, there is a possibility that there is one scenario that we called 1D scenario. So in similar samples, it has been found that on the surface steps, there is, on some of them, there is very largely increased density of state. And the presence of this largely increased density of states takes place only on the steps which are odd. So on even steps, like 2 atomic planes, there is nothing is seen. It has to be 1 or 3 or 5 or sort of in this order. Our samples do have steps. I mean, I was showing you that there's a perfect quality of this surface. So this is AFM studies. So this is how they look in this planar view, and this is the cross section. So these are atomic steps. So we certainly have atomic steps. So we cannot exclude this possibility. However, we try to make standard transport samples, and we didn't manage to detect any superconducting signal. So in summary, I just wanted to convey you a message that in this class of material, zero bias features are ubiquitously observed. They are clearly connected with the topological phase of these materials. They are not present in trivial case. Actually, they go hand in hand with magnetism. So when we introduce magnetic ions and the system, when it turns to ferromagnetic fields, the features are even stronger. This is still very interesting and still awaits full theoretical explanation. They could be related to this one-dimensional conducting channels along the steps, but at least up to now we are not able to confirm this. Thank you for your attention. Well, you know, when we saw them for the first time, of course, our hopes are very high because it looks like you know, this fancy Majorana-like states. However, we did our best, conversely, to prove that these are not. So what is the best explanation? I think that this one-dimensional edge channels could be a good source. However, what is still puzzling for us, we are not able to find this one-dimensional superconductivity which would run across the surface of these materials. So, I mean, these materials are somehow unique. So maybe this is really something odd that really has to be actually developed by theory. We don't know. I mean, my favorite would be this one-dimensional channels, but as I said, we also failed in this case to prove that this is the case.
Okay, thank you. Other questions, maybe, comments? Yes, I see one hand.
The peak in DIDV that you interpret as due to the Majorana bound mode, did you try to interpret this peak as Andreev type transport in the point contact that would inevitably have such a shape like that?
Certainly, you're right, but the point is that if you want to invoke Andreev reflection, we have to also, at the same time, introduce superconductivity. So that's why we wanted to find the superconducting phase in this material anywhere, and we didn't find it. So this is the point. I mean, this could be the simplest explanation, but we needed superconductivity for Andreev reflection.
Actually, I have two-part questions. One, I didn't follow exactly your explanation why we have to exclude pressure effect in this case, because in one sample you did observe it, in another you didn't observe, and you made a conclusion that the pressure effect is excluded in this case, which was not clear to me. So I would want to hear a little bit more about that. And second question, second part of my question is there is pretty much number of samples where we can see enhanced by point contact TC in the materials which do not actually show the superconductivity by itself, or show the superconductivity at much lower temperatures, which is observed in case of point contacts. Could it be the case in for your samples?
Yes.
For example, like tungsten carbide, it is not superconducting by itself, but in point contact, in soft point contact as well, people do observe superconductivity.
So as I said, I mean, concerning to the second questions, still the jury is out. So we don't have a final explanation, and as you said, it may be something something like this. Concerning the first question, I mean, could you actually rephrase it once again? So, which case you didn't? A pressure effect.
Yeah.
Ah,
yeah.
Oh.
Why actually you stating that if you do not observe the superconductivity in one case and observe in another,
so-
you can exclude the pressure effect?
Okay, so what I wanted to say that because we have a large number of samples which were either trivial or topological, and we use exactly the same method to create point contacts for both of them, and none of the trivial samples show these features, none of them. And almost all showed from this topological origin. So the point is, if in our method we are introducing, so if this was the, if it was due to our method that, let's say, that pressure effect introduced this zero bias conductance peak in the topological material, so then, so then we should see it also in the trivial case. And in the trivial samples, we didn't see it. So it's not the method. We made this soft point contact on the to the two classes of samples in exactly the same way. And on one class, there was no effect whatsoever. We tried hard. Even in one cases, no. In the other, or in almost everyone. So our conclusion is it is not pressure. It is not. On the other hand, this is just a, I mean, we didn't use any tip, anything like this. We just put a very gentle. Yeah, but also in the, but only in the topological crystals, not in trivials. So then. So maybe we can just, okay, yeah. So,
Question, or may I ask you a question, or you continue?
I think that I should see these effects also in squid magnetometry, if I just had. Maybe not sufficient. I said we boosted up and we tried, I mean, we did our best. So, I mean.
You said there is no superconductivity on a macroscopic scale, but can you exclude the superconductivity on a microscopic scale as, say, inclusions of
You mean
lead or tin or whatever? Did you try to
I mean,
study?
we checked everything. We checked the wire, we checked the silver paint, we checked everything. Okay.
Interesting discussion, but it seems that you may have the two-dimensional superconductivity on this surface, which is not found by the magnetometer.
Okay.
And this, in this case, it may be Andreev reflection origin of this zero bias peak.
Okay. Possibly yes, but it would be fantastic because then this superconductivity would exist only in this topological sample. So it would be topological induced superconductivity, and this would be something. I mean, we did a lot of, we tried to do transport one way or another. I mean, we didn't find any superconducting signal in transport measurements. So we believe that if there is two-dimensional superconductivity somewhere on the surface, I'm pretty much sure that we should have find it. We didn't.
Okay, you go on. Mike, I am supposed to give you this. Okay, okay. Maybe camera is pointing out, I think. Nice.
Thank you.
Okay. Okay.